Hi all, this is Mr. Yeager for Physical Science. We are starting the unit on heat energy, on thermodynamics for physical science. Not a very long unit. It has a couple important little topics that we're going to go over. Today we're going to go over what is temperature specifically, and then we're going to look at the definition of thermal energy and what affects thermal energy, as well as specific heat. So we got three things: temperature, thermal energy as a concept, and specific heat. So to introduce this unit, this heat energy, thermal energy, it's all under this umbrella of a topic called thermodynamics. And basically we're looking at the relationship between transferring heat and energy between these different objects. We don't look at the concept of work too much in physical science in relation to heat. That's a broader topic in thermodynamics and physics. So again, we are really just looking at this idea that thermodynamics is how heat is transferred. So we're looking at how energies move from one area to another area, from one object to another object. Okay? So the first thing we have to understand is, what is temperature? So temperature itself, we know, if we mention what's the temperature, what does temperature measure, most people talk about how temperature measures how hot or cold something is. The thing is, how do we get a value for that? I mean, I understand that we could sit here and be like, hey, it's 85 degrees out at Fahrenheit, and we know that means it's warm. But what is that actually measuring? What are we actually talking about with temperature? Okay? And again, this is what's just kind of saying it. Obviously, when something gets hot, the temperature is higher. Okay? So why is this? Temperature itself, what it actually measuring is what's called the average kinetic energy of the particles. It's talking about how quickly those particles are moving. So if I increase the temperature, I'm increasing this kinetic energy of the particles. And again, kinetic energy is the motion of the particles. All right, it's related to how fast they're moving. So a higher temperature means those particles in the air are moving faster. That's why you feel hotter, because they're colliding with you and transferring that energy. All right, so that's what we're saying. As the temperature goes up, the speed of those particles goes up. Okay, the way we actually measure temperature in science is with the unit called Kelvin. All right, Kelvin itself, we use the Kelvin because Kelvin ends at 0. The lowest temperature for Kelvin is 0, and there's only positive temperatures. The other one that we use in science quite a bit is called the Celsius scale. We use this because it's based on a factor of 10. The problem with the Celsius scale is it can go negative and positive. So the reason a lot of scientists like the Kelvin scale is when there's 0 Kelvin temperature, all the motion has stopped. Okay? All the particles have stopped moving. This is called absolute zero, if you've heard of that before. So absolute zero is where all particle motion completely stops and there's no energy. The thing is, on the Celsius scale, when you're at 0 degrees Celsius, all right, there's still kinetic energy. But that's where that's where we struggle with this idea a little bit sometimes, because how can there be a negative energy? We're not saying there's a negative energy. It's just how the scale was made. All right. The other nice thing about these two temperatures or units is 1 Kelvin is the same thing as 1 Celsius. Fahrenheit, the one we use in the United States, that one has a fraction involved, 9/5 degrees Celsius plus 32. So, I mean, that one's a little bit more funky to look at. I think we are going to look at it briefly today, though. Yep, here we go. So, Kelvin is equal to Celsius, okay? The thing is related to Celsius. I shouldn't say it's equal. We have a formula. Kelvin, if we want to convert from Kelvin to Celsius or Celsius to Kelvin, if I have Celsius, what I need to do is add this 273 to that temperature, and that's how many Kelvin I have. So what I mean by that is, if you have 0 degrees Celsius, and I say how many Kelvin is that, it's 273 plus 0 equals 273 Kelvin. Okay? So when I'm at 0 degrees Celsius, I'm at 273 Kelvin. Again, where did that all come from? It's just the way the scales were made, so that's where it's a little bit funky. The other formula that we will be practicing in this unit is converting Fahrenheit to Celsius. So I already just mentioned that one out loud one time. Degrees Fahrenheit equals 9/5 times the degrees Celsius plus 32. So a little bit of a funky formula. It'll be given to you so you can use it appropriately. But again, this is just how we relate different measurements in temperature. Okay? So they all measure how fast the particles are moving. Kelvin's the only one that can't go negative. Fahrenheit and Celsius can go negative. All right? So if we try to practice this real quick, what is the temperature in Kelvin? If I'm at 50 degrees Celsius, I would do Kelvin equals 273 plus 50. So this would equal 323 Kelvin. That would be my temperature in Kelvin. We do have to write K after it. What's the temperature in Fahrenheit? All right. If I'm trying to do Fahrenheit, it's degrees F equals 9/5 times 50 plus 32. So 9/5 times 50 first. 50 divided by 5 is 10 plus 9, or plus 9, sorry. 50 divided by 5 is 10 times 9 is 90. 90 plus 32 is 122 degrees, not Celsius, Fahrenheit. Okay? So 50 degrees Celsius is a scorching temperature if it's weather, 122 degrees. That would be something you might feel in like the Sahara Desert on a very, very hot day. All right, so that's where we got it. A few more practice. Water is at 350 Kelvin. What is the temperature? So for this one, I would do 350 equals 273 plus degrees Celsius. Subtract the 273. And let's see if I can do that in my head. 77 degrees, right? It would be degrees Celsius is 77 degrees Celsius. Okay? 350 Kelvin, 77 degrees Celsius. A healthy person has a body temperature of 98.6 degrees Fahrenheit. Ooh, this one I might have to go grab the calculator. 98.6 equals 9/5 degrees Celsius plus 32. Subtract the 32 first. So that would give me 66.6 equals 9/5 degrees Celsius. That's an unpleasant number, but yep, 66.6. Grabbing the old calculator. I would then multiply that by 5 and divide it by 9. You'd be 37 degrees Celsius is my final answer. So normal human body temperature is 37 degrees Celsius. All right, I hopefully think that's all the practice. Yep. All right, so second topic, brief one here. So that's temperature, measuring the average kinetic energy of particles. Then we have what's called thermal energy. Thermal energy is looking at the total amount of energy basically in those particles, the sum of the kinetic and the potential energy of those particles in a substance. Now this we're not going to really calculate. This is going to be more of a concept of how do I get more thermal energy, how do I have less thermal energy. But thermal energy itself is just basically how much energy is in those particles themselves. It's not necessarily just the heat, but all that energy saved up in the bonds and everything. Thermal energy depends on two things, temperature and mass. The nice thing is they're both direct relationships. If I increase the temperature, I increase the thermal energy. If I increase the mass, I increase the thermal energy. On the test, what we would do is be like, you have a cup of water at 37 degrees Celsius and a cup of water, same size, cup of water, at 30 degrees Celsius. All right? If I have these two temperatures, which one has more thermal energy? We would say the first cup of water that's at 37 degrees Celsius. That has more thermal energy. All right? So they won't ask, like, the big thing here is we will relate two different objects. We'll either adjust the temperature and keep the mass the same, or adjust the mass and keep the temperature the same. So a favorite one, I believe, is this one right here. Which has more thermal energy? This iceberg or these ice cubes? Well, they'll both be at 0 degrees Celsius. The thing is, the temperature is the same, but what's different? Mass. The iceberg has a huge mass. The ice cubes have a small mass. Because there's more particles vibrating at 0 degrees Celsius, the iceberg has a higher thermal energy. Okay, has a higher thermal energy. So it's not just about the temperature, it's also about the mass that we got to pay attention to. All right? So again, the more the kinetic energy starts moving, the more the thermal energy goes up. If I increase the temperature, I increase the thermal energy. Okay? So that's basically it. I mean, and this is just telling you, obviously, as the temperature goes up, the thermal energy goes up as well. Okay? More kinetic energy, more thermal energy. All right? Next concept, heat. Okay, what is heat? Heat itself is thermal energy. It's just another word for thermal energy, but we usually use this word when we're saying that the energy is moving. There's a flow of the energy. Okay? And the heat is where something's going from a higher temperature to a lower temperature. Heat always travels from high temperature to lower temperature. Okay? That's the thing. It's always measured from higher to lower temperature, or not measured. It always moves from higher to lower temperatures. Since heat itself is energy, we do measure it in the unit called the joule. Okay? We use the unit the joule. So heat is measured in joules. I want to take a quick step back to this one more time. Heat always goes from higher to lower temperatures. All right? I always use this example. If you go to a big pool and you jump on in the water, okay, you might say, this water is cold. It's making me cold. That's true. The water is making you cold. But the idea is, cold doesn't move. Okay? When we say cold, we just say it doesn't have a lot of heat. What happens is when you jump into the pool, your heat leaves your body to try to heat up the pool around it. It's trying to make everything in the same state, equilibrium. Okay, it's trying to put everything into equilibrium. Since you have more heat than the pool does, your body will release that heat. When your body releases the heat, you will feel cold. All right? So that's what's happening. There's no such thing as cold energy. All right? There's no such thing. I'm going to write it out and then cross it out. You know, you always see that. There's no such thing as cold energy. It's heat is leaving you, which makes you feel cold. Your body now has less energy. Again, this energy is measured in joules. All right? Always flows from warmer to cooler materials. So we have a measurement because some objects release and absorb heat faster than others. And we call that specific heat. When a substance absorbs heat, its temperature will change depending on what it is. It depends on the substance itself. Think about what heats up fast. Okay, if you have a pot of water and you start the burner, what heats up first? The metal. Why is it heating up first? Because of what it is versus the water. Okay, so the specific heat is describing the object itself, what it is, the nature of the object. Okay. So the amount of heat that's needed to raise the object, and we always say with 1 kilogram, this is very standard, the amount of heat needed to raise 1 kilogram of a substance, 1 degree Celsius, is called that object's specific heat. This is, as the name kind of implies, specific to the substance. Specific to the substance itself. All right? Very, very, very specific to the substance. All right? Specific heat has the units joules over kilograms times degrees Celsius. Okay? Per kilogram, it says Kelvin, but this can be degrees Celsius. Okay, they're the same thing in the end there. Okay? So, when you change the thermal energy, the energy is going from hot to cold, and it'll flow into or out of the object. All right? We use the symbol Q for thermal energy. Q stands for thermal energy or heat. These two things are interchangeable. All right? We have C is the specific heat, so that's a constant. And then we measure it by doing a formula. I'll rewrite this. Q equals M times C times delta T. What's this all mean? It says it down here. The change in energy, the change in thermal energy, the heat, is equal to the mass of the object times the specific heat of the object times the change in temperature. Change in temperature is equal to final temperature minus initial temperature. All right? So we have to have all of this information. It's going to be probably the most intense of all the formulas we use in physical science. It has the most numbers involved. But in the end, after we subtract the temperatures, final minus initial, this can be positive or negative. You just multiply it by the mass and the C, and we can get the amount of heat. Heat can be positive or negative. All right. We're going to come back and do a couple problems in just a minute to show how those are done. To measure specific heat, to measure thermal energy, we have an instrument called a calorimeter. It's like a big thermos. It's a very, very strong thermos, okay, as you can see there, an insulated flask. This is the instrument we use to measure heat. It's called a calorimeter. That's pretty much all you need to know. Okay? What we usually do is an object is placed inside the inner barrier. We burn it. Basically, we catch it on fire, we let it burn, we look at how much energy changes, and then that way we can then, based on the mass that it has, and as long as all of it burns, we can figure out the specific heat of the substance, because then we know the mass, we know the temperature, all right, and we can, we would already know the specific heat of the substance. We know what this substance is. We can find how much energy is released by that substance. So we know the mass, we know what it is, the specific heat. We would find the temperature change with the thermometer and solve for heat. Okay? So here we go, ending with some question. How is temperature related to kinetic energy? Temperature is the measure of average kinetic energy. Oops, sorry, I went a little fast there. It's the measure of average kinetic energy. I'm fine if you were just remember that temperature is kinetic energy, a measurement of the kinetic energy. All right? How is thermal energy related to kinetic energy? In other words, as one goes up, what happens to the other? If I increase kinetic energy, I increase thermal energy. They're directly related to each other. Question 3. The amount of heat that is needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius is called the specific heat of the substance. All right. All right. I'm going to take it back. I want to do one problem with you. Okay? One specific heat problem. Let's say I have a 2 kilogram object that has a specific heat of 4 joules over kilograms times degrees Celsius, and that is heated from 10 degrees Celsius to 20 degrees Celsius. How much heat is absorbed? As this is going to be the only formula for this unit, well, I shouldn't say that. Sorry, you have all the temperature ones. This is the biggest formula for this unit. You will know that you need to use Q equals M times C times delta T. So M is mass. There it is right there. So it's going to be 2 kilograms times the specific heat of the substance given to you, 4 joules over grams times degrees Celsius, kilograms, sorry, times change in temperature. So this is the only mistake I see people do when they start this. They'll sit there and be like, which one should I use, 10 or 20? Neither. You don't use 10 or 20. What you got to do is we got to subtract these two. This is the initial temperature, this is the final temperature. So the change in temperature is 20 minus 10, which equals 10 degrees Celsius. Not that 10, this 10, because I already subtracted them. If this was 5, my answer would have been 15, okay? So then I plug that on in, 10 degrees Celsius, and I basically just multiply. 2 times 4 is 8, times 10 is 80. 80 joules of energy is released. So that's basically it. So again, we went over temperature, thermal energy, and specific heat today. This is a new formula that you're going to be practicing with, and there we go. Thanks.